Hello, I'm TJB Chris. In my last video, I surmised that I would not be following on to the expansion project for the Model 12. I had just completed the 7-slot backplane, married it with my card cage, and thus far it is a marriage made in heaven. I figured I could leave well enough alone and we'd just move on to something else, but momentum is momentum, and what can I say? I'm excited about expansion in diagnostics, and I love building things. So we're going to follow on to that video with the natural progression to the diagnostic spacer, which we will build and try out, and its close friend, the test fixture, which we will again build and try out. In addition, we will pair the test fixture with the backplane already installed. So join me out at the bench. We're going to take a quick look at the documentation and we're going to start building this. And then once we're done, we're going to get the Model 12 involved and we're going to break a couple of cards out and maybe the oscilloscope to show you just how much easier your diagnosis can be, your development can be, when you can bring the bus outside of the machine without even having to take it apart in some cases, or if your machine is already apart, allowing you to break things away from the chassis and have the room you need to work. So let's get started. Join me at the bench. And here we are out at the bench. It's the cold side of the basement, and though it may be April on the calendar, it doesn't really feel like it. And also, thin kid me is cold me, so I'm going to wear my best non-Mr. Rogers sweater here and just be old man about it. So either way, let's start with the first item I'm going to be building. That is the diagnostic spacer. And as noted in the documentation, and as I've noted as well, the diagnostic spacer serves two purposes. The first is to allow you to bring the bus master and interrupt chain up to the next slot should you remove a card, therefore not breaking the chain. And it also allows you to bring out the Z80 bus to outside the machine for the test fixture or other purposes. In addition, it does have the requisite power status LEDs and resistors, which we will be installing. And according to the documentation, it slices and dices too. I've not tried to slice with it, but I guess I could see it. Either way, I will not be slicing and dicing with this because it will be used in a computer. This is going to be a pretty straightforward build. I'm not going to populate this 80-pin header here. I generally tend not to, especially since this is primarily going to be used for my purposes for using the test fixture, which will give me access to those lines outside of the system. All right, is there anything else that we have to take a look at? On the documentation, there's straight up 40 by 40 headers. I got the keyed headers again, and this is really because I want to make sure that when I plug in keyed cables, I don't mess them up on either end. And since I used keyed connectors on the backplane, I may as well use the keyed connectors here. I plan to use the same keyed connectors on the test fixture. And if I say keyed one more time, I don't know what I'm going to do there. And so I think that pretty much covers it for the diagnostic spacer. Let's get right to building it. And there it is, diagnostic spacer complete. We have our resistors and requisite LEDs for power status. We have our bus master and Z80 interrupt chain jumpers, and we have our extension connectors to bring the bus out of the machine should we so choose. And of course on the back, near the wonderful Tandy Emeritus logo, I really like that kind of build on the Tandy Corp hourglass. We have the solder joints that I did. I'm pretty happy with those, especially since halfway through I ran out of my .032 diameter solder and got stuck with .05. Same formulation, but it's not a bad solder, but it was a little big, but I did manage to make it work. I just had to be extra careful. I've got more of the other one on the way. Anyway, next up, let's get to the test fixture. And when we get to the test fixture, it's important to note that not all the components go on the same side of the board. On the backplane and on the diagnostic on the diagnostic spacer, you can put all the components on the same side of the board. The silkscreen on the backplane indicates otherwise, as I noted in the last video, but it doesn't really matter. It matters. So this is designed so that if you look closely, you can tell that the silkscreen with more detail. So for example, look at the amp connectors here. See these lines? The additional lines? If I flip this over, you're not going to see them. You're just going to see an outline. So this indicates that the side with more detail is where you should install the component. And that's because most of the components should go on this side of the board, where you see here, except, so for example, the amp connectors, the resistor networks, right? You can see the lines for one. I don't know if you can see those, but they're there. You'll notice though that the outline here is here for the power connector. The same goes for the 40-pin connectors here, and that's because, flippity flip, on the back of the board you can see the outlines. The power connector should go on this side of the board, and these connectors should go for the bus on the back side of the board. Why? because the bus and power should be able to plug into the back of the board, and then on the other side, that's where your cards go. You have to put the components on these sides. So you have to pay close attention when you're building this if you want this to line up right. You need to make sure that you're putting the components on the correct side of the board, and the silkscreen is your clue. One more thing, on this board it says component side, and you'll notice that it says it on both sides. You're saying to yourself, but TJB Chris, how is it that the components can go on both sides of the board? Well, either you are a very clever solderer, or more importantly, you'll know that this is in reference to the component side of the plug-in card. When you plug in, for example, a video card or a hard disk interface board, the component side of the board you're plugging in should go in the direction of the component side text. So for example, if you're plugging in a video card, the components on that video card should be up, solder side should be down. Okay, and that's if the component side is up. Very important, thought I'd point that out. We'll take a closer look at this when I get it all built. All right, let's get on to building this. And jump cut to a different shirt and shorter hair, and that's because it's been a couple of weeks. Things have been busy. Anyway, let's take a quick look at the documentation on the test fixture now that we've covered some of the caveats of building it, silk screening and everything. And you'll notice on the page on your screen right now one of the two configurations at which the test fixture can be found, and that is with a 3D printed bracket designed by the designer of the test fixture and the diagnostic spacer. And that leaves it in this orientation with the cards coming in, and there's card guides and all that great stuff. The other one, a couple of pages forward, has you arranging it slightly differently so that you can essentially lay the board down and stick the cards straight up in. And this one, if you're not doing too much on the cards, attaching too many probes or putting too much weight on them, can work for you, but generally speaking, and I'll get more into both of these mounting situations later, I'll show you both. But generally speaking, I'm going to go with option A, which is the stand-up version, because I think for my use that's going to be more convenient, and that gives me the opportunity to be a little more pokey with the scope and make life easier for me. Okay, so let's take a look and see if there's anything else we need to know to build this. I'm just going to go forward another page, and by the way, if I go back one page, you can see the test fixture in use, all built, and you can notice, you can see on here, just as I was talking about, jumpers on one side, slots on one side, but you can see from the solder traces here that on the other is that the connectors are on the other side. So we're going to pay close attention to that orientation as we get to building this. And you can see also on your screen, this is the designer's system. Is that a 6000 or a 16B? I can't remember now. Shite. He told me too. Fark. Well, I don't remember, but either way, it is either a 12, 16B or 6000. I'm trying to tell by the case. Oh, well, it wouldn't be a 6000 or a later 16B, because if it was, the CRT could still be attached, because the later systems had the back cover that just come off. So this is likely a 12 or an earlier 16B. Okay, now that you watched me reason that out, let's go to the next page and take a look again. This is it fully assembled, and that's what it's going to look like when I'm done with it. And you can see below that the diagnostic spacer, which we've already covered. So the basic instructions for this still apply. Soldering iron, correct temperature. I'm using 350 because there's not large ground planes or anything else that I have to overcome, so I don't want to overheat the board. And we're actually going to start with the 80-pin amp 2x40 card slots. Let's get to that. And here we are, connector installed, correct orientation, pretty happy with the solder joints there. And I think now we're going to do the bus connectors here that connect to the diagnostic spacer or to the expansion bus connectors on the backplane. And there we are, we've got our expansion bus connectors installed. And in the order of operations department, I didn't really consider that I should have put these two on after I put these two, because having these in place already made these solder joints a little tight. Not too bad, the iron fit in there just fine, but in my zeal to do let's do the big stuff first so it looks cool, mindset, I got ahead of myself. So planning is very important, folks, when you put these together. Prior planning prevents piss poor product. Sure, why not? Alliteration is cool. Either way, it worked out, I got it, but I will have to be more careful in the future. All right, now I'm going to do the rest of the part components. On this side, we have resistor network sockets, and we have jumpers and capacitors and such. Let's do that. And there we are, the completed product. As usual, I didn't populate the top header here. I don't usually, and there's additional auxiliary power connectors that I did not bother with right now. Figured extra pins sticking up is just something that I'm likely to catch. But we have our resistor network socket. I've got my jumper pins installed for the Busmaster and Z80 interrupt chain bypasses. Of course, we've got our amp connectors installed. Optional power connector, which I won't be using for now, but it is there for future expansion. And I figured I would do that now while I'm here. So this is pretty much it. Now we're going to talk about mounting. And there are, as I mentioned, two different ways to use this. You can use either this bracket here, which allows you to set the card like this so that you can plug the cards on the top, or there's a side mount bracket. So we're going to talk about this one first. I'm going to assemble this and show you how it works. You're going to need to use both sets of these brackets, M3 screws and nuts. I'm using this. Use metal. You're outside the machine this time, so use metal. I didn't use metal in the machine because if they come loose, I didn't want something to fall. And you'll want, for the other test fixture mount, for the side mount here, you're going to want an M4 threaded rod, not unlike the inanimate carbide rod on The Simpsons that won Employee of the Month, and wing nuts, again from the documentation. So, those are M4 wing nuts, obviously. So, let's get started with this. I'm going to start with this mount first. I'm going to move the camera a little bit, and we're going to put this together and see what it looks like. Alright, so how do we orient this? I've got my screws here, I've got my nuts. You might want to use washers on here. So the way that this works, actually, you can see I've got this kind of indented side down right now. It actually goes the other way. So set like this, card sits on top. The idea here, and I'll show you, is that the cables, the bus cables and such can extend out the back. Now you're not going to be using the optional power connector if you're using this mount, of course. But that said, it's pretty straightforward. We just run the screws through and line them up. And we attach the nuts, and I'm going to do that now, and we'll come back to the fully assembled version. Here we are all assembled, and good to go. So, card slots up. You can see in the back here the groove and indentation. Bus connectors here for cables to exit the back. And of course, you won't be using the power connector in this situation. And this works pretty simply. You simply take your test fixture, and you install your card here, played by a 68,000 memory board here from the 16B, and actually you just insert it into the slot. Now, very important point, this card does have pin 1 marked, and the test fixture also has pin 1 marked. It is critically important that you line these up and make sure before you apply power. If you don't, you're going to send 12 volts someplace you don't want to, and you're going to blow up a piece of computing history. So be sure that you install this correctly. And in fact, the way that you can kind of get this is, and this is actually given away by the component side again that we talked about earlier. So just as a double check, if you line up the component side, your pin 1s will line up. And now we're installed. And now if I spin this around for you so you can see, I could very simply, cables would be exiting here to either the diagnostic spacer or the backplane, and I can attach my oscilloscope probes, my voltmeter, whatever I want to do, poke, prod, work with this card while the machine has power and make sure that it is functioning properly. So with that, we're going to move on to the way that I plan to use the test fixture, and the way that I think will be more convenient for me and that allows a little more weight to be put on the cards. Actually, important point there. Make sure that with this, you don't put too much pressure on the card. You could create a bit of a problem here if you put too much weight on the card. You could damage the card or the slot. So just be careful there if you're using this. But this is a great way to kind of do this, keep it compact, and do some basic diagnostics. All right, let's look at the other mounting method. And now the other mounting solution. This essentially makes a small card cage outside of your 8-inch system, and it works like this. Test fixture basically just attaches to the outside of it, and you get a mini card cage. Great. So let's put this together. The first thing you're going to need, actually, and if you see the lighting has suddenly changed, I went and got the big guns. So there will probably be some different reflections, but at least you can see what the hell I'm doing. Anyway, you're going to need 4 of these PCB guides. These are the same PCB guides that I used on my 3D printed card cage, so the part number should be up on your screen right about now. And these just snap in place, so the fixture has holes already designed or already put in there and aligned to these particular parts, so you just snap them right in. That's all good. And then what we do is simply, as I kind of demonstrated, attach the test fixture, cards on the inside, to the 3D printed sides here, and the test fixture goes in like this. When I first showed you, I kind of had it on the wrong side, but this kind of goes in like this. So let's get this attached, and then I'll show you what it looks like and what the next step is. And there we are, mostly assembled. And there's, you can see I got my ring light back there. And there we are, test fixture attached to the board. Again, make sure you put the board on the inside of the fixture here. You can see the overlap. Apologize for the ring, I'll try and avoid that. But there you go, that's basically how we have it. So now it sits like this, but we're not done yet. So what you need to do is this M4 threaded rod, Employee of the Month, actually goes right through here. And what you do is we use wing nuts on the inside and outside to tighten this and give it some rigidity, but it also gives us some adjustment ability. So what we're going to do here is I'm going to thread 2 of the wing nuts on kind of backwards onto the inside of this, and then I'm going to put it back into the test fixture here, and we'll do this the other way around, get the other wing nuts on there. Let's go. Okay, wing nuts in. I think I got these in far enough. So we're going to just do this. We're going to slide these in. Probably went way too far in on those, but that's okay. And I'm not going to tighten these up because I want to put a card in to line them up. So let's just do that. But before I do that, just to get myself ready, I'm just going to slide the other wing nuts on here. And these go on the what I would call the correct way, assuming that I can line my hands up. Okay, good. That one's threaded, cross-threaded. There we go. And there you go. You can see I got a little play here. Let's grab my 68,000 memory card again. Slide her in. I can use the top slot here, and as you can see, we're way too wide, but that's okay. I'm going to slide it right into the socket here. Okay, there we go. And now, we'll do that. These guys will tighten. You guys will go a little further. Once you dial it in, oh, look at that. See? And that's the beauty of this system, right? There you go. So now, 68,000 memory card out. This is the assembled test fixture. Apologize for the ring light. But that's it. Adjustable spacing, easy to build, 3D prints very nicely. This is my preferred configuration for this, and it also allows you to use the power connector if you have to do anything with that. I think it's time that we take this in, connect it to my TRS-80 Model 12, test it out, make sure it works, and all that good stuff. So we're going to do an actual diagnostic case on this and show how it should be used. Join me in the computer room. Back in the computer room, we have a plethora of items: test fixture, diagnostic spacer, cable, and cable? Voltmeter, bourbon. Because of course, bourbon, very important. Okay, before we get started, I've got a lecture for y'all. Sorry, gotta be done. So we have not 1, not 2, but 3 cables for a very important reason. We in the trade have a habit of calling these 40-pin ribbon cables with the IDC female ends IDE cables. Everybody does it. I've done it. You've probably done it. The documentation for these various items do it. Because from an everyday standpoint, this is what we work with. They're used in IDE functions. These are straight through cables. There is nothing fancy about them aside from the fact that it is a ribbon cable with a crimped on IDC connector, female in this case. Why am I talking about this? Well, because this here is actually an IDE cable. And let's take a closer look at these two cables side by side. So on the left, I have a cable that clearly, if my camera will play nice, has more conductors than the cable on the right. Yet they have the same number of pins. Let's look at it this way, shall we? We have 40-pin cable, more conductors, that's 80, folks. Not as many conductors, not more conductors, that's 40. What's the difference? Well, these are just IDC-ended ribbon cables with 2x by 20 female connectors on them, what we call IDE cables. This is an IDE cable. It is an 80-conductor IDE cable. It even has color-coded ends. Why is that? What's the difference? Well, and this is going from some serious memory, but you're going to start to find these cables as you get into the mid to late 90s and into the 2000s before serial ATA came along. And they're very important for a lot of reasons. It's mainly important because around that time, Ultra DMA drives started to come out with higher throughput levels than we were used to with traditional IDE or parallel ATA. To make this possible, they had to reduce the amount of crosstalk between the various conductors carrying the signals for the drive. And to do so, they inserted a ground conductor between each of the data carrying and signaling conductors. So you've got pin 1, pin 2, like conductor something, ground, read, ground, write, ground, whatever, right? You get the idea. Now, that by itself isn't too much of a big deal, but there's also an important point. I mentioned the color coding. So this blue is the host end, and then these here are for the drives. This cable allows for a built-in cable select, gray, black, but also a way to tell the host that one of these cables is in use so that the host knows that it can enable UDMA modes that require this cable. I want to say it's UDMA mode 2 and up require 80 conductor cables or it won't work. So how does the host know, or the machine that this is installed in, the host, know that it is in fact a UDMA capable cable? And that's because in addition to the additional conductors which are just tied to ground, some additional conductors in this cable are also tied to ground. And those are pins 2, 19, 24, 26, 30, and 40, at least from the source I've got in front of me. And as you can now see by the picture on your screen, those pins map to things on the Z80 bus that are important. If you just map those to ground, it ain't gonna work. Now, near as I could tell, the 5, 12, and minus 12 volt lines are not directly mapped to ground, so you shouldn't get a direct short. But at the very least, if you use one of these 80 conductor cables with this, it will not work. So don't just go pillaging some late 90s, early 2000s machine because it has the end that looks right. At worst, you could damage cards, the machine, or both. Okay, sorry for the lecture, but it's very necessary. Do not use 80 conductor IDE cable. This is actually an IDE or whatever cable for Ultra DMA. Okay, love Chris? Good? Okay, let's get back to this now. With all this in mind, there are essentially three main configurations that you'll find using this, as I mentioned. The first is the diagnostic spacer by itself, where were I to remove this hard disk interface board, for example, which I'm actually going to do because we're going to want to do that later. Okay, hard disk interface board removed. Now, I have gone and done my worst Fleetwood Mac and I've broken the chain. I said I wouldn't, but I've done it. But I can fix it. And the way to fix that is by putting jumpers on these two jumpers here and inserting the diagnostic spacer in that slot. And that will bring, as I mentioned, the two chains up to the next card, thereby keeping the chains intact. And in addition, I have my LEDs here, so if I had a backplane that did not have the Tandy Emeritus 3 power LEDs on there, I could get power status just from this. So just by itself, the diagnostic spacer is a very useful item. The second configuration is the one that we're going to be examining tonight, and that is the diagnostic spacer in conjunction with two of these 2x40 IDC female-ended quote-unquote IDE cables, and connected to the back of the backplane, which is the scenario we're going to demonstrate. And the third is the test fixture connected to the two 40-pin connectors on the backplane back there. And I'm not going to demonstrate that tonight. And actually, there's a reason why, even if you have the backplane, you wouldn't want to do that. Why is that? Well, that's because with the way the interrupt chaining works in the Busmaster, if you want to diagnose something that is a higher priority than the cards in the system, you're going to want to use the diagnostic spacer to insert yourself into the interrupt chain before the lower priority cards. You need to be able to put yourself at the right spot in the chain, and that's why even with the backplane, you may need the diagnostic spacer. So let's talk a little bit about wiring this up, and then we'll verify what we've got, and we're going to test this out. A little bit closer now, let's take a look at the back of the test fixture. I have here J5 and J6. And J5 is the pins 1 through 40 of the Z80 bus. J6 is pins 41 through 80. Similarly, on the diagnostic spacer, I have J11 and J12. J11, let's turn that so the light's not messing it up and get my fingers out of the way. J11 is pins 1 through 40 on the Z80 bus, and J12 is pins 41 through 80. So what you're going to do is connect J11 to J5 and J12 to J6. So let's do that now. Here we are connected, J11, J5, J12, J6, all set. And of course, I use keyed connectors here. I recommend you do the same, but you have to be careful because if you use a keyed connector and you've got like this, one of these cables with the strain relief on it, you may run into situations where it's a little tight. Like I might run into that under the video card. It should fit, it looked like it would fit, but you want to be careful about making sure these aren't, either your cables don't have the strain relief and or your ports on the board are shallow. But I like and recommend keyed connectors. That way, other than getting the bus wires backwards, it's almost impossible to screw up. Well, anyway, with these connected, I have them hooked up, both keyed connectors on both ends. There's an easy way to test. Before I connect this, I want to make sure that I've got pin 1 here and pin 1 here correct, all the way 80 and 80. And the reason for that is because if I get these backwards, I could shoot plus 12, plus 5, or minus 12 volts somewhere on the bus that I wouldn't like, and it could blow a bunch of cards in the motherboard. So again, diligence is key here. So I'm just going to set this down. I'm going to break out my voltmeter, and we're going to set it to the annoying beeper mode. And the way that I look at this, if I have pin 1 to pin 1 and pin 80 to pin 80, I'm good to go. So here's pin 1. There's a little square there. Pin 1. I'm going to hold that there, and I'm going to hit pin 1 here. And we have the annoying beep. Same goes for pin 80 here. And by the way, the pins are labeled on the board. So I'm just going to... All right, pin 80 to pin 80. And again, and they are, you may not be able to see it in the camera, but the pins are numbered 1 to 80. And actually on this, they have all the nice little numbers. So I'm confident that I can install this into my Model 12, not create any issues. I've looked at it under the magnifying glass like 5 times to make sure I didn't cross any solder joints. Okay, I've temporarily put the hard disk interface back in the slot because I want to be able to show you the LEDs here. Now, in this case, because I have the test fixture connected, I have not put the jumpers on here. I need the chain, Busmaster and Z80 chain, to make it out to the test fixture. So for this to work, I can't jump them here. And then out here on the test fixture, I have jumped, according to the documentation, the Busmaster in and interrupt chains in and out, JP2 and 3. That's loop always. That will always just send the chain back to the bus. And there's no cards above it, so it won't matter too much, but just for the sake of doing it right, this way, with the test fixture plugged in with no boards in it, the interrupt chain will come out to the test fixture here and make its way right back to the machine. I'm going to plug her in. Okay, I think we're ready to power this up. I am going to try my best not to make life miserable for y'all and take you off the tripod. We're going to walk around and see if we get an insert diskette prompt. All right, here we go. Moment of truth. Okay, I heard the floppy seek. That's good. And we've got an insert diskette prompt. All right, let's go look around it back and see what we've got on the diagnostic spacer. Okay, you can't really see it because the cables are in the way, but the reflection gives it away. You can see that we have the plus 12, minus 12, and plus 5 volt LEDs there. And of course you can see the backplane ones shining bright on the top there. But the diagnostic spacer is working correctly, and it appears to be bringing the bus out to the test fixture. So now I think it's time that we go through a real-world example of what you might want to do with this. And we're actually going to take the diagnostic spacer from slot 3, we're going to move it down to slot 1, and the hard disk interface board, if my camera will focus. I got a new camera, folks, and it is the same brand as my last one, but it is a little bastard when it comes to focusing, so I need to figure out if it's got some pretend intelligent crap. Anyway, hard disk interface board going into the test fixture, and we're going to break out some stuff, and I'm going to walk you through the too long didn't read version of a problem I'm having with another piece of hardware, and we're going to show you exactly what the test fixture is for. Okay, hard disk interface board removed, and in its place you can see I've got the ribbon cables going over into the Model 12, where the diagnostic spacer is putting them in the correct place in the bus. This is a higher priority than the video card, so therefore it goes in slot 1 and the video card has returned to slot 2. Now that we have this out, of course you'll remember I mentioned that I had the 0 card configuration set with JP2 and 3 in place, just looping the interrupt chain back. Well, to put cards in this, that's not going to work. Now, in addition to the one configuration of, hey, I've got no cards, there are 2 other configurations, according to the documentation, that's going to be up on your screen right about now. And that is, first, there's a 1 card configuration, and there is a 2 card configuration. In the 1 card configuration, your first card always goes into J0, which is the first slot, and that's card 1, as also noted on the silk screen. Then, if I'm going to only use 1 card, I jump 1 to 2 and 1 to 2 on JP7, and is that JP1? There we go. So 1 card, 1 to 2, 1 to 2 on these sets of jumpers down here. If I have 2 cards, now I put both cards in, of course, after I set 2 to 3 and 2 to 3. So you only need 1 pair of jumpers no matter what, despite the fact that there are 4 headers on this, because at any given time you're only going to need 2 jumpers. Well, I'm going to use the 1 card configuration, so I'm going to jump 1 to 2 and 1 to 2, or as the silk screen says, 2 to 1 and 2 to 1. I'm going to insert my hard disk interface board into my newly built test fixture. Oh, I got it in there crooked. Now you gotta be careful because you can't get these crooked. There we go. And there we go. Now we have, I'll just back this up a bit, a card ready for diagnostics. I'm going to do myself a quick favor and make sure the machine fires up. Voltages look good by the LEDs. And I have myself an insert diskette prompt again. No need to drag you all the way over there. You can probably see the light coming from inside the machine. So there we go. We've got the interrupt chain properly jumpered because we're getting back to the video card and I've got a video on the screen. All right, off goes the Model 12. Now, let's take a look at the scenario. This is a 15 meg disk system that I got. It's one of those drive and controller combinations that Radio Shack used for various systems. The Models 1, 3, 4 had them in the 5 meg machines. There was an 8 meg one for these machines that had its own interface board. And then there were 12, 15, and later 35 and 70 meg drives, and probably some other sizes I'm forgetting, that used the interface board I have, the 1215 interface board, also sometimes referred to as Type 2. This could be its own video. I'm not going deep into it here. If you want to see that video and want me to go into the problems I'm having with this and submit your thoughts, let me know and I'll walk you through what's going on with this. But for the purposes of diagnostics, this isn't working right, and I need to do some diagnosis on it. And I'm not sure if my problem is with this machine and the controller card within it, or if it's with the interface board. So this has its bubble replaced with the DREM, which I will show you in due course. And then we'll take a look a little bit at the kind of diagnostics you can do with it. I'll show you very quickly what it's doing, and we're going to get back to the test fixture because that's why we're here. So I'm going to show you what's wrong with this, and then we're going to come right back around to the test fixture, probe around, and I'm going to show you just why the test fixture and diagnostic spacer are such great additions to any Model 2, 12, 16, 16B, or 6000 system. Let's take a closer look. All right, as you can see, the drive bubble is a DREM here. I've got a good image. So basically the short version of this is if I take a known good image, say from the DREM that's in a similar disk system in my Model 16, put it in here, and run the diagnostics on it. And I have run the alignment on this. So again, if you want to see the video of this diagnostic alignment and the problems with this drive, it's its own video. I apologize for skimming over this, but this video is going to be long enough as it goes. The issue here is, in the diagnostic, it'll read, write, format just fine, works just great. When I go to use it, it doesn't play so nice. So let's just do this. We'll go to hard disk alignment, and I'll do drive 4. And let's just do here configuration, as long as I know what I've got. For actually 153, there's more cylinders than that. There are 4 heads, so I should be able to work with this. And if I do a random read X, you can see it's very quickly reading the tracks. I've got the alignment dialed in pretty nicely, actually. I'm pretty happy with that. And in fact, let's select, I'm sorry, I want to seek tracks. Yeah, select seek. I want to seek track 0500. I will do it with verify, and we completed successfully. So it seeked the track and it read the track, so that's good. Okay? And now I will write the track. Yes, I want to use this track. I'll just do a single pass. Write complete. Now this doesn't tell you much because it could say write complete. It sent the command to the controller. The controller ostensibly sent it to the drive, but we don't know if it actually worked yet. Or space. Okay. The keys you using this? There's a manual and I should reread it. Anyway. Okay, so now let's try and read this track back. We're still on track 500. I'll do a continuous. You can see it is very happily reading from the disk. So from the diagnostic standpoint, it seems to be working great. Now, formatting can tend to be an issue. Format diagnostic track 1. It'll seek it for me. F. Says seek diagnostic track formatted successfully. We're on track 1. Now let's do a read test. Continuous. And yet again, it seems to be reading pretty happily here, passing each test. Now, if this wasn't working right, it would sit here and say status, whatever, and then it would give you something, ID not found, bad CRC, something like that. There are a bunch of errors, but this seems to be working fairly well. Okay, well, so here's the issue. If I try and actually use this with an operating system, say Tristos, what ends up happening is the controller will essentially, with the controller of the drive, something is basically seeking over and over again to the same spot. It's though it's restoring the head and reseeking. So let me demonstrate that. Okay, let's try and boot the Tristos image on this SD card. So I know what you're saying. But TJB Chris, didn't you just wipe right all over that disk with the diagnostic program? Yeah, you're right, I did. But I just replaced the image with a good one from my laptop that I know boots because it's from my Model 16A over there. Okay, and the DREM is powered up, and you can see we have an additional screen. Look at this. This is connected to the DREM. All right, so let us do this. I'm going to power this thing up, and we're just going to kind of let it go, do its thing. And the first thing you'll notice as the machine comes on, it hasn't said insert diskette, and in fact, it is sitting here, and there it goes, it just did the floppy seek. There's no disk in there, it's reading from the hard drive, and now it's waiting, and now, here we go. It's almost like it's retrying. Very slow seek. And then now, I don't know what the machine's up to. Now, there it goes. It's like a slow seek, repeat. Slow seek, repeat. And it's hard to describe, but that long form seek should not be happening. And it does complete all of the reads. If I let this sit here long enough, the machine will boot Tristos very, very slowly. And the funny thing about this is, when I did this in the diagnostic, it didn't do this. So I'm not exactly sure what's happening. Other than doing the alignment on this and making sure that all the technical bulletins are up to date, I haven't done a whole lot more on this. But again, this could be its own video. So that's what the disk is doing. Now you see it's not quite working right. I'm going to bypass doing the checks on this because A, I've done some of them, and B, that's not this video. And I'm going to go back to the interface board on the test fixture, and we're going to take a look at the flexibility offered to us to diagnose the hard disk interface board via the test fixture. Oh, for those of you watching who just love pain and punishment and overthinking things, and yeah, that's a 64K color computer in the background. Look at that. Ain't she party? Anyway, this is the 8X300 controller. This is the wide board controller. So for these hard disk units that went into this particular hard disk interface board, there are two different styles of boards, especially in the 15 meg drives. There are these older 8X300 boards, and there are Western Digital boards. And the Western Digital boards are easily identifiable by the fact that they take up half the size. They're half the size of this, so they take up half the real estate. This, of course, is the larger 8X300 board, and I've read that these boards can be problematic. So the problem is probably here, but I'm going to use this as an opportunity to demonstrate what happens when you have the ability to remove a card from the machine and play with it. So let's take a look at this hard disk interface board and see if there are any test points we can probe and take a nice look at that. And here we are with the scope setup, and this is the perfect setup for the test fixture. I've got the machine running, the diagnostic is running the D-run adjustment, so to do that it does a constant read on the diagnostic track, so it is doing its thing, the controller is doing constant reads, and that means we've constantly got data going over the bus. So I'm just going to check out here, IC12 should give us some level of activity. I'm going to use my right hand because I'm right-handed, and if I short this thing out, I'm very unhappy. And let's just get this. I'm going to hit the auto button because it's easier when I'm doing this one-handed. And there we go. I've got obvious activity here. This is probably 20-pin IC, I think. And we've got something on pin 18. Similarly, down here we have another one. Let's just pull this out a bit. And you can see we've got something going on. So across the IC, oh, actually, nope, that was just me. I'm just going to probe around. Yep, and of course, now again, I'm not going to get into what is happening on here because that's not the point of this. But the point here is I can check out any of the particular points on the card. Be careful because the machine is running. I can also check out any points on the bus because I have the bus header here. And having chosen not to populate that actually gives me a good place to poke this. So, I mean, honestly, just in the diagnostic sense, you can see that with an oscilloscope and a card here, or a card pulled out of the machine, with the machine in a diagnostic state, I now have access to everything I need to be able to poke and prod this card and make sure that the thing is working correctly. And of course, if I'm prototyping or anything like that, this gives me a great opportunity to work on a proto board, do what I need to do, modify the circuit, power the machine up, assuming that there's no smoke or going to be any smoke, and passes all the non-smoke smoke tests, and I should be good to go. And so this really kind of demonstrates the flexibility. You can bring the bus of your Model 12 out of the machine to allow you to work on it, probe it, whatever you'd like to do. This is the perfect use for the test fixture. And again, with a hard disk interface board, I actually needed the diagnostic spacer to get it in the proper place in the chain so that I could actually make this work the way I want it to. And from the thick of the fun, right down here next to my oscilloscope, the test fixture connected to my TRS-80 Model 12 where the hard disk diagnostics are currently running. That's going to do it for this video. I hope you enjoyed this. I really wanted to walk you through the test fixture and the diagnostic spacer. I know I was going to do something else, but I thought momentum is momentum, and this was a great opportunity to show you what these were capable of. I know I glossed over this, but this is its own video. I could do an hour on this hard disk thing I've been chasing. So if you'd like to see that, let me know. Otherwise, I have some non-8-inch system plans in the immediate future. I keep saying that, but I really do. And then I do have more Tandy Emeritus greatness to bring your way. I've got the Z180 adapter and another surprise that I'll be bringing you down the road. But until next time, I am TJB Chris, thanking you for joining me. Again, solicit Tandy Emeritus, and I forgot to mention, Tandy Emeritus has a website. You can go to tandy-emeritus.org. That's tandy-emeritus.org. Check out information about all of these without having to watch me blather. And their email link is right there, so you can get in touch with somebody at Tandy Emeritus and get your order in for hopefully all of these great pieces of hardware. So until next time, I'm TJB Chris. Thank you for joining me. I will see you in the next video.